Hi, everyone. I'm Susan Nash, AAPG, and I'm just really excited that we have a very interesting and illuminating presentation today. I know a lot of you are very involved in interactive, well, simulations and in AI and machine learning, that you're wondering, okay, how does it all come together? And so today we have a really interesting presentation by Jean-Marie Laigle, who is going to talk to us about interactive Earth modeling. So just like to say welcome, Jean-Marie.
Thank you, Susan. All right. Okay. So let's start. So the topic today is interactive Earth modeling. I am going to walk you through some techniques that we are developing here at Explore Lab to make Earth models much more accessible and extract more values from them. So just a little bit of clarification about what we mean about interactive Earth models and what are the promises of this model. So we aim to have a representation of the subsurface and its physical state that we would like to be able to interrogate or query at any time, but also update for any scenario when the data change or when the interpretation change. So it requires the ability to rapidly update the state of the model as new information is available. But also it requires to be able to produce models ensembles rapidly, make it this affordable in order to evaluate uncertainties on which decision, which will impact decisions. So over the last decade, there's been a lot of effort to explore machine learning techniques in order to automate and accelerate the workflows which are useful to build geological models. So I'm on this schema listing a couple of techniques, and there are probably much more. It doesn't mean to be a comprehensive listing here. Some example of application of machine learning to accelerate seismic interpretation by automating faults or geobody speaking, accelerate the construction of velocity models. So all of this relate to seismic data. Regarding wealth data, machine learning is used for petrophysical interpretation. And there is also all of the range of application to extract value from documents by automating extraction of knowledge from document databases. All of this in order to build sound and valid geological models that are going to be simulated with a numerical simulation to update the physical state of the subsurface, which is used to perform place and prospect evaluation to inform parameters for drilling, before drilling, and during drilling. Also, they are useful for development planning and monitoring. So there's been a lot of focus on accelerating the construction of the geological model, but it only delivers its full value if the simulation is fast as well. The fully interactive model is going to require to solve the simulation bottleneck, so updates can be propagated rapidly when a change is applied in the model, when a new interpretation is available, when the user wants to evaluate a new scenario. And this is what we are going to focus on today. What does it take to develop a very rapid numerical simulator with examples that I'm going to provide for the field of basin modeling and how we can accelerate thermal simulation and pore pressure simulation at basin scale with a speed which is orders of magnitude faster than existing technologies. One very important aspect that I want to emphasize, which help to understand the value of building this interactive model, is about the quantification of uncertainties. And this is something which has been recognized since the industry's building models. This is an extract from a paper from Hicks which has been published in 2012, highlighting that successful decision based on models in which significant uncertainties exist requires that the modeler is able to identify and quantify uncertainties, propagate these uncertainties from input through output, and also clearly communicate this information to decision makers. And the current way of building models doesn't fully allow to meet these three requirements. And some pitfalls, which are quite common, is not keeping the goal of the model in mind as it is built to direct and focus the appropriate levels of effort during the model construction, not clearly identifying which uncertainties will have significant impact on the results, ignoring uncertainties because you don't have enough time or do not have the knowledge on how to adequately handle them, working hard on issues that you're comfortable of working on, or not recognizing feasible alternative scenarios. And most of those pitfalls usually stem from the fact that building these models require a significant amount of effort. And because of the time and the effort you invest in building this model, you tend to stick with a limited range of scenarios. Most of the time because it's either impractical or not feasible in the time frame allocated to actually update this model to recognize other possibilities. So Earth or basin models are fundamentally integration tools, and making them interactive is what is going to allow to reduce uncertainties. Some of you who are familiar with this field will recognize that evaluating the chance of success of an Android prospect, evaluating a play, evaluating the volume in place at a certain location, or predicting the state of the subsurface before drilling, all requires to be able to model what is a complex interplay between components. And there are many unknowns and degrees of freedom. The subsurface is mostly unknown. And so this is why we build physically and geologically valid model to test hypotheses. And this building process is something which is quite linear, and updates, iteration are difficult, mostly because the simulation is a bottleneck. So this is why they are often built quite late in a project, because waiting for all of the data to be ready before doing the actual simulation. And also because building them requires effort, they deliver only a limited range of answers. So how do we improve on this? So the current approach is to obtain the physical solution from for a geological model. I mean, there are two categories. They have their advantages, their drawbacks, their supporter, and their critics, just exposing here the approach and the strategies. There is an approach where, which consists in solving the physics at sparse locations, so building 1D model at key location, calibrating them to the data, and then building a full model by contouring the solution obtained at this specific location. So this puts a lot of workload on the geologist who is going to be in charge of designing a solution which makes sense for the basin. On the other hand, there are what's called full physics basin model, where we are going to provide a complete physical description of the subsurface, and usually in a 3D mesh. So because this is a lot of effort to build a mesh at basin scale, the resolution of this model is usually quite coarse. There is a very large number of parameters to inform, because you need to provide all of the parameters for the partial differential equation at every single node in the basin. And each iteration is going to require to rebuild the mesh to rerun the entire model. The map-based approach is more nimble, more flexible, but there is a lot of manual effort which is involved in order to obtain a solution. So both approaches have in common that obtaining the physical solution is actually a lengthy process. So how to make it more interactive? So we believe that if we are able to solve the simulation bottleneck, we are going to unlock a lot of new workflows and possibilities. And when this is solved, it requires, in a second step, to build a technology stack which allows for the continuous integration of data and updates of the model. The benefit of having a very fast basin simulator, or the promise, is to maintain evergreen models, to deliver simulation insight very early in the process, even while we are building the model. You could even think about having the simulation directly available on a seismic interpretation platform, for instance, allowing a very fast rerun for sensitivity analysis and exploration of the solution space, and also being actionable by non-expert. In order to do that, we are going to use machine learning as a numerical method to get the solution of the partial differential equations that govern the physics in a basin. Machine learning is a tool which is used in other fields, specifically for this problem. Here are some examples of articles, and there are many more. This is a growing field. And there is a range of techniques which are explored to accelerate solving the physics with machine learning. Here we are going to use it as a method to estimate the solution of the PDs which are used in basin modeling. So there are unique challenges for basin modeling, especially the fact that we model the basin through time, and so the mesh evolves through time, and the physical properties of the mesh also change through time. This is one of the fundamental equations in a basin model, which is a heat equation. It's not a very difficult equation. It's not complicated. It's diffusion. It has a smooth solution. It's a well-posed problem. It's transient, meaning that we model the solution through time, and time is a parameter there. It depends on properties which, as I was saying, evolve through time. So, for instance, the conductivity of the rocks, the bulk thermal conductivity is something which changes with the porosity, which changes with the burial. And so there is all of an interplay of parameters that needs to be accounted for when we try to solve it with machine learning techniques. So there is a range of approaches which are explored for many different problems. Here we have tailored a solution to this challenge, which is specifically designed for the problem of solving temperature, maturity, pressure, compaction in a basin. So this is a generic machine learning-based basin simulator, which implements the same physics as a classical simulator. It can be seen as direct replacement for a classical simulator. It has the same inputs. It's going to deliver the same output. So you could see it simply as a new type of solver. And it's an end-to-end approach which learns the mapping between a high-level description of the basin, of the geological model and its boundary condition, and the physical solution. So a deep learning approach, which is a shortcut for the entire process, which is usually implemented of starting with a present-day description of the basin, making a restoration of the basin through time, usually using a backstripping approach, applying boundary condition and solving step-by-step the physical state until obtaining temperature and maturity through time. What we have demonstrated here is that it's possible to design a deep learning approach which does an end-to-end mapping between the description of the basin and the physical solution. So how do we do that? We are going to learn from simulation examples, which are generated by a classical forward basin simulator. And the key here is to design a training data set, which is going to be, which is going to encompass all of the possibilities in terms of geometry, stratigraphy, sedimentation rate, lithological description, boundary conditions that you can expect in basin on Earth. So it requires to define boundaries which are large enough so any geological situations that we can find in the Earth sedimentary basin is actually covered. So we are actually learning from a space which is an hypercube, and we have developed a function that can transform a point which is inside the hypercube into a geological model. We're going to simulate that geological model in order to obtain a physical solution, and develop that well a database of basin simulation, which is perfectly adapted for the training and which provides actually a perfect training data set. So it offers the guarantees that most of the geological models that you can design are going to fall somewhere into this hypercube for which we have learned what is the corresponding solution. So what is the physics which is actually implemented? This is basically the same physics that is implemented in the forward simulator, which is used in order to provide the training data set. So talking about here the solution for the heat equation, that's the solve of the heat equation in an evolving mesh, which describes the basin geometry through time, which is informed with lithologies, boundary condition, and a full lithosphere model, down to the lithosphere-asthenosphere boundary. It accounts for radiogenic heat production in the sediment and the crust. It accounts for the possibility of rifting and the timing with the Mackenzie model. The geometries are restored through time with the backstripping process, which takes into account erosion and compute maximum burial for a sedimentary column. So boundary conditions are typically a temperature at the sediment-water interface and at the base of the lithosphere-asthenosphere boundary. And all parameters that you can put in your model can vary spatially and through time. And it's possible to include additional physics if that's needed, such as diagenetic processes for reservoir quality evaluation, or of course, source rock maturity and organic matter transformation. Example of the training and validation, I'm showing here cross plot, which shows a correlation between the values which are delivered by the forward basin simulator, so the classical simulator, and the prediction of the machine learning based simulator. This is an example for 50,000 1D model, which were not used during training and which are uniformly distributed in the training space. You can see that there is an excellent correlation. The error of the machine learning based model, the error distribution is very narrow. It is centered on 0. This is exactly the type of behavior that you would like to obtain when training for this type of problem. And this is a comparison between the machine learning based model and an industry standard simulator. That's a synthetic model, a uniform column, 20 layer, 500 meter thick each, deposited over 40 million years, all shale. So something really generic. You can observe that there is a fantastic agreement between what's obtained by the machine learning model versus an industry simulator. The difference is that the industry standard simulator takes a few seconds or tens of seconds to get this result. The machine learning based model take 1 microsecond. So that's 4 to 5 orders of magnitude faster than what you can expect from a standard simulator. And this is where it starts becoming incredibly helpful to update rapidly a model. And I'm going to demo this to you in a second. Right. Going to show an application of this using a regional model of the Gulf of Mexico, which has been developed by Andy Pepper 2022. This is a cross-section through the model from actually Arkansas to Mexico in the Yucatan. That's a very regional transect, 2,000 kilometers long. Showing here the full lithosphere. So this is a lithosphere-asthenosphere boundary with 1,300 degree isotherm at the base, a crust which varies in thickness, and also a radiogenic production which varies in the crust. Where there is oceanic crust, the radiogenic production is 0, and a number of key surfaces for the sedimentary basin. So the source of the heat in this model is isotherm at the LAB depths and a variable crustal radiogenic production there. So let's see what it looks like here in the platform. So I'm going to show you the rapid simulation here. Just a couple of introduction on the framework in which this happens. We were mentioning at the beginning, building interactive Earth model required to solve the bottleneck of the simulation, but it also requires to have a technology stack which empowers people to perform this rapid update and to operate this fast simulation. So all of the graphical elements that you see here at the screen are part of the technology stacks that is needed in order to make this actionable. And one key component is actually to have a true geographic information system in place through GIS for the rapid integration of data that can come from different sources and eliminate all of the pain of converting this data to a common CRS and so on. So this is a geographic integration tool specifically oriented for the modeling that you see here at the screen. And so this happens. So this is Gulf of Mexico, as you can recognize. This is a database of almost 40,000 wells, all of those dots, which have been used to calibrate the model. And I will expand on this after the demonstration of the simulation. So here I'm displaying the model. So this grid that you see here at the screen, this is the bathymetry or the topography. The model that we are looking at is a stack of grids. So you have horizon. So this is the first layer. This is the top Miocene. This is, for instance, the top Cretaceous, which are available there. And there is a number of properties in each of the layers. So that's actually a 3D model that we are looking at with properties such as the mineralogical composition, but also properties which are computed by the simulator, such as the temperature, the thermal stress, pressure and porosity, and so on. Right. So what does it take to actually run a thermal simulation of this model? Simply move here into the simulation panel and click on this run button. I'm going to do that. We are going to wait a few seconds for the model to update. When this will have happened, it would have been the equivalent of running this as a 3D model with an industry simulator process, which can take hours. So clicking here on this run button, so the simulation is progressing there. As you can see, the spinner takes just a few seconds to finalize. And here is an updated model. So it has now been informed with, for instance, temperature data here in the late Cretaceous. So this is what we are looking at, the distribution of temperature in the late Cretaceous. This is a distribution of temperature there in the mid-Jurassic to mid-Cretaceous layer. Looking at another key property, which is standard thermal stress as a proxy for the maturity of source rock. So this is what's been just computed in this mid-Jurassic to mid-Cretaceous layer. For those of you who are not familiar with this color code, blue means that if there were a source rock in this layer, it would be immature. Green means it's an all window gas in the red window, and gray would mean that it is over mature. So now let's consider that because there are uncertainties on so many things, we want to update this model. So there are here a couple of sliders which are exposed in order to start varying parameter. For instance, varying the depth of the asthenosphere, which controls the position of the 1,300 degree isotherm at the base of the model. Let's make this like 20 kilometer deeper. So like moving the slider and clicking here on the run button. So what we expect is actually having a model which is going to be cooler in the sense that the depth of that isotherm is deeper, right? So what we are looking at here is a direct consequence of applying this change. If you had noticed in your mind what was the distribution of the color on the previous stage, it's now significantly cooler. And we can look at what it gives as a 1D extraction at some locations there. So I'm going to here add a viewer to perform, looking for instance at the temperature. So you can interrogate the model wherever you want. This is, for instance, the temperature profiles which are extracted from the model, and comparing this with some observed data. So we're going to load an observed data set. Right. And plotting here some temperature data, something like this, right? So what you see here, we have extracted the temperature profile at that location that I have picked. This is a nearby well, actually at 2.5 kilometers from the location where I have picked, which has some raw temperature and corrected temperature there. And the model is a bit too cold compared to what is observed at this location. So you can simply try to start updating this by, for instance, by bringing the base of the asthenosphere a little bit closer to the sediments. So getting back here to a scenario where it's actually closer by updating the depth globally for the entire model and just running a new simulation there. And as a consequence, we are now matching better this data, but everything has been updated globally. It's not just 1D simulations that we have done there. We have actually an entire new scenario. So calibrating this well by well is, of course, something that a modeler typically does when he produces a scenario. And this slider here lets you appreciate what is the variability that you can expect. It doesn't make necessarily a lot of change at this location, but this is something that can have dramatic consequences far away in this example in areas that were in the oil window in the previous model, which now can be in the gas window, for instance. So because the simulator is so fast, there is also an opportunity to automate the calibration of this model to observation. So this is something which we've done in this example where we have been inverting the radiogenic heat production in the crust at each of those wells locations. So that's almost 40,000 temperature records that were used for the calibration of the RHP from a public database, with a strategy which has been first to optimize the depth to the asthenosphere boundary in areas where we know that the RHP is going to be zero because this is oceanic crust. And then from there, focusing on optimizing the RHP in the transitional to continental crust. So this entire inversion process is something that takes only 40 minutes with such a simulator, using only one CPU core, because you can compute a simulation in 1 microsecond. You can actually afford the optimization problem. This is typically something that would have taken weeks with conventional tools, or require an enormous amount of power to do so in an affordable time. Right, and just to continue to show some results here of this, this is a best case for the standard thermal stress for this model in the mid-Jurassic to mid-Cretaceous layer, right? So some things that we can obtain in seconds, as you've seen, and this is an evolution of the thermal stress through time. So we are here during the Cretaceous, and you can see how thermal stress evolves during burial as the basin develops. That's also something which is an output of this type of simulator. So these are typical output for a classical basin simulator, and it's a very fast ML-based simulator deliver actually the same, right? In order to continue to expand on this, we are building tools to accelerate also the migration of hydrocarbon. Solving pore pressure and thermal stress is just the first step. We want to be able to understand migration pathway, understand accumulated volumes and risk for oil and gas exploration. And with the same philosophy, we are developing rapid tools which are going to allow to do so. And as I was talking about building a toolkit for operating these models, there is also some thinking about what does it take to actually empower people to extract more value from these models by accelerating simulations. Something that I have highlighted is the fact that it needs to be a true GIS with a first-class support for gridded data, because we handle this data on grids. So this is something which is not commonly available as a lightweight toolkit to fill the gap between GIS tools and geomodeling tools, and to have the ability to integrate data and make operation between this data and independently of their mesh, resolution, coordinate system, and so on. So things that this solves this bottleneck. It has to be a flexible platform for the implementation of new tools and algorithms. So this is an evolving field. We have seen in the very first slide that with a lot of effort, which is put on accelerating the construction of geological model, and this goes through the development of different versions of machine learning models, different groups proposing solution. And so there is a need for a platform which can host this continuously evolving algorithms and allow people to have access to them first, but also to test and compare them. So that's certainly the requirement of what a modern software should have. We believe that it needs to have an open API, so a fundamental function of the software can be accessed and even accessed remotely. So the user interface is not the only way of interacting with the software, which makes it possibly integrated into either other toolkits or into services which automatically update data. Shouldn't have any lock-in in an internal database or formats, but instead use standard industry format. I don't think that there is any need to reinvent the wheel on this. Gridding is something which is a fundamental need, and as I was mentioning, being the ability of handling grids which have different coordinate system, different mesh, which comes from different tools, and be able to format them in a way which is consistent is a fundamental requirement of the technology stack in order to action the simulator which is behind. And there is also a lot of value of offering a catalog of data set which can be readily integrated into projects. And there are many of those data sets which are publicly available, and especially for activity explorations, integrating data from different sources is something which is key. And that's something that a platform aiming at developing interactive models should actually offer. Right. So some remarks in conclusion. There is a tremendous value in accelerating physics simulation, because this is what can really unlock the entire process of integrating data, interpreting this data, obtaining a physical state of the subsurface, and using it for decision making. And because this is something which is so uncertain, it has been recognized long ago, but we cannot stick with just one scenario, one model. It has to be a way of updating it as easily as possible. And this is the goal of building this interactive Earth model. It definitely unlocks new type of workflows, like building these models early and getting results while you still interpret or build the model. So making this available in the seismic interpretation platform, for instance, can be a very powerful application. Auto calibration to observation and building evergreen models. There is no need to wait for more data in order to build the models, and there is no difficulty in simply integrating a new piece of information when it gets available. You simply replace it into the model building tool and just simulate it again and have your result instantly. It offers the possibility of doing high resolution sensitivity analysis. And down the road, when integrated with other tools, you can get early recommendation while building your models, like does this data make sense? I mean, does this temperature data points that I have is consistent with my vision of the basin, and so on, which are things that you usually discover down the road, but much later. And with a very fast simulator, you can get access to these insights very early. It empowers geoscientists to integrate all data to rapidly explore scenarios, update models, and test ideas, and importantly, focused on what is really the most impactful. We have seen so many cases where there was these ideas. The amount of erosion is something which is really important in this case to explain observations, the maturity of source rocks, and so on. And when you start building models, you realize that it might not actually be the most important, because the maximum burial is still not as important as the present day burial or things like this. So having this insight very early, for instance, can help you to direct your efforts in areas where they are most needed. What I have shown today are applications focused on exploration or appraisal type workflows. And similar application can, of course, be developed for field development and reservoir management. And some in the industry are working on this. The focus today was more making this available for exploration workflows. Right. Yeah, I guess, Suzanne, this is what I wanted to show today. So I'm happy to answer questions now.
Oh, great. Well, let's see if we have some questions in Q&A. So Marianne Love Malinconico is asking, can the model include advective heat flow effects, for example, gravity topographically driven across basin fluid flow?
Okay, so possibly yes, with the same approach, but the current version of the simulator is a diffusive heat flow. In a future version, I mean, and this is not the first time that we have this suggestion. This is really something that we can focus on. So for now, it's the version which is in production and has been tested and validated is for diffusion.
Excellent. Okay, Patrick Ing asks, how to best incorporate risk assessment with model updates and idea test?
So that's a really good point. And I think that the first step to do that is to think about how the result of a model are used in a risk assessment process. So what are the criteria which are evaluated for risk, and how the model helps to evaluate these different criteria. And then that's basically linking this into the mechanics of the risk assessment workflow. So testing IDs, understanding the sensitivity on some parameters, this is what fundamentally this type of tool is for. You have one best scenario, which is with the default values of your data. And with this slider bar that I have shown, and here are exposed some parameters, but there are many more which can be exposed. You can basically move and test the model for any new parameter set. And this is where then it goes through risk assessment, evaluating things like the risk of related to the maturity of a source rock. Try to move your parameters to the boundary of what is acceptable and see how this is going to change. In some areas, it might not change at all. So that can tell you something about the risk related to this. In some other areas, it can be extremely sensitive. And that can also help to guide the acquisition of new data that can then help to reduce the risk.
So thank you. That was really a great answer. Good questions too. So when I was looking at the Gulf of Mexico model that you gave us as an example, all I could think of is like some of the challenges that people have when they are developing their field is figuring out the connectivity, especially in deep marine clastics, connectivity of different lobes. And yeah. I was wondering if your models are effective at that, or if this is more, or if this is just larger scale.
No, it can be any scale. There is no such thing as a large scale or small scale. This, as long as the physics which is applicable for these problems that you mentioned is the one which is implemented in the simulator, there is no scale issue at all. I mean, I was showing something which is very regional. but it can be also very local and high resolution. Actually, we've done many local studies with this type of tool, including in the Gulf of Mexico.
That's really interesting. So for example, you could use it for developing ideas of the different types of fluid within a reservoir and different connectivity, even fluid flow.
That's right.
Interesting. Well, so we have some time. I'd like to encourage people to open up their cameras and microphones and go ahead and ask questions, because I noticed there are quite a few people in the audience who have worked with machine learning and with simulations. And I just wondered if people might have some interesting insights from their own experiences too. So Dahl Winters is holding up her hand. Dahl, would you like to join in?
Sure, happy to. I have a question about, or just, I guess, some general thoughts about your use of tiling. I've in the past I worked with geospatial big data, and I know that for applying machine learning models for land cover classification, it can be a problem to have models that are applicable throughout. Now, given that it's a physics simulation, one can control for that. So I'm curious if tiling has been an issue for the workflow, and if it hasn't been used yet, whether it could possibly provide some advantages.
Can you just expand a little bit on this? So I get exactly what you mean by that.
Sure. So, for example, Uber has an H3 tiling scheme, basically at each zoom level. If you think in terms of zoom levels, on a large scale, you have more data, and then as you kind of zoom in, you can get finer resolution. Of course, when dealing with tiled data, raster-based data, gridded data, I guess we're mentioning the same thing. Those data you can apply a model to a very small area, say like around your well. But if you're wanting to simulate larger regions, do you have a tiling scheme in mind? And if so, like, is it, I guess that's, I'm just curious, has that, is that approach for you?
Yeah, okay, I understand better. I mean, as long as the physics which applies to the local scale is the same as the ones that you want to model at a larger scale, so far we didn't find the need to actually tile the data because of data volume. And we basically simulate everything. I mean, we've done simulation with more 15 million grid nodes with reasonable times. But that might also be due to the specific problems that we are solving here, where the model delivers prediction in basically 1 microsecond per sample. So that gives you a lot of bandwidth, actually. So to answer to your question precisely, for the type of applications that we have been looking at, we didn't find the need to actually tile it. You can certainly conceive the need, but that would require actually so high resolution models that we have not been facing them already. So it has just been manageable so far.
Okay. Well, that's very insightful. You've done an excellent job with advancing state of the art in physics simulation and geoscience. So, I just know from an alternative approach using probably less data than you're dealing with geophysical simulations that, on terabyte and maybe close to petabyte scale, these models sometimes, if you can train a model for a very small area, and that model will not be applicable that easily to an adjacent area. And that has been an issue before. But given the nature of seeking to provide physical examples for training data, I think that eliminates a lot of the uncertainties that are present in replicating the actual dynamics of what happens. So really happy to see that that's incredible work. Thank you so much.
Thank you very much.
Yeah, thank you. Oh, that was a great question and great response. Prasad said, great talk. Extending Susan's question is a simulation integrated or simulator integrated with mud models. I guess
yes,
I
am reading and there is an additional comment below, so I'm just looking at this right now.
Okay, perfect. Oh, right. Well, I guess the question is can you integrate in mud models?
Up to a certain point, yes. Then to answer to this precisely, would certainly need more details about the resolutions that you're looking at and the physical processes that you're looking at as well. But to a certain point, yes, we do integrate with mud models. And we've done that already in studies. Yep.
Nice. So I have a kind of a nuts and bolts question. So you're dealing with enormous amounts of data, right? Like, are you talking about a petabyte or?
Well, I mean, there are different things here. The first one is the data set needed to train this type of model. And
Yes.
these are synthetic data that we have
Right.
generated ourselves. So we have a full control on the training data set distribution, which is key to make this generic and applicable in most of the basin. I'm not going to say every basin because geology is always full of surprises. But the rationale is to try to get this as generic as we can. And so this is why we have generated the training data set ourselves to have this full control. So that's quite a voluminous data set in itself. Not talking about terabyte here, but definitely in the order of hundreds of gigabytes of data. Then there is the application of these two models, which can to Earth models, to geological models, which can be actually quite high resolution now because of the speed factors that this trained machine learning algorithm delivers. And so if this is too high resolution, it also certainly poses a challenge in terms of data management and the strategies, for instance, either for simulation. We have not faced that problem that much right now, but also for visualization, which was part of the question before. How do you visualize efficiently in a GIS-based environment a model which has tens of millions of nodes? And so there are other type of challenges there that we are working on that I have not described today, but this is certainly a different category of challenges.
Exactly. And so I'm thinking about it's not just the model and the assumptions and the data, it's the data management. So, I mean, are you using like Databricks or Snowflake to help with some of the
We're not.
Oh,
That
okay.
might be useful, but so far we didn't do that. In terms of visualization, it's more about presenting in the field of view of the user the information which is needed in the most efficient way. So that requires possibly tiling at some point. That requires also all of the work on, for instance, blending the color in the view. So you give some kind of estimate of what is the representation at a point where it might exist some data, but you cannot just present it for memory reason or whatever. So there is a lot of a range of strategies that we are working on to make the exploration of these models as fluid as possible, independently of their size. In terms of data storage and management, this is not something that we are actually working actively on. So far, we are not using any type of service or database like Snowflake or others for actually hosting this data. This is something that we mostly rely on what the companies would like to do. And that's not something that we're trying to solve.
Okay, that makes sense. So you're assuming that a lot of the stuff is so yours is flexible enough to deal with other companies' own data, data strategies or data management systems.
Right.
Super interesting.
Yeah, this is a completely different category of problems, and so this is not the one that we are focused on.
Yeah, it's not really the geology part, but it's fascinating to me because, like, it's interesting that the data scientists really need to work really closely with the domain or discipline experts in order to make sure that the data is used in the correct way. And it's just so fascinating. Patrick Ng kind of alludes to that in his comment. It's really interesting comment that you commented on earlier.
Yeah.
Well, we have time for one more question. And I just want to remind everyone that you will be receiving an email with a link to the recording and also a link to register for the next one. And we have a really, really interesting next meeting too. And it's on April 9th. And the topic is the final frontier of deep water exploration. And it's Paul Mann. So get us all excited about OTC and also and then continuing on sort of the things that you've been talking about, just the new Earth models and new insights. So he's going to be focusing on the South Atlantic mainly, or continent ocean transition zone of rifted passive margins. So not necessarily South Atlantic, but he's going to be focusing on the Atlantic. Any final questions, anyone, or comments? Well, Jean-Marie, I want to thank you very much for just a really wonderful and informative webinar, and just really, and Patrick King has some really nice comments. Thank you. He says,
yes, thank you.
Well,
thank you, Patrick.
This is really great. Yes. And I'm just really excited that we have such an opportunity for exploring really the cutting edge that really everybody needs to know about it, because modeling and interactive modeling is just right on the cusp of a huge breakthrough. And the fact that we are able to manage data in ways that we could not before is really a game changer. But thank you, Jean-Marie. And if you have any final thoughts.
No, thank you, everyone, for for your participation, the good question and interactions. And you can always reach out to me by email or on LinkedIn if you have any further questions or comments.
That's wonderful.
All right.
Well,
Thank you so much.